Hi, I'm Jay.
And I'm Sarah.
Welcome to the FM1 tutorial.
Today we'll be talking about drag reduction by wake interference.
In this video, we're going to be discussing what we saw in the FM1 lab in more detail, and we're also going to go through section by section what we expect from you in the lab report. Yeah.
Okay, so before you start your reports, each of you should have a copy of Mr. Blob's communication guide. So we highly recommend that you have this communication guide next to you while you are doing your reports, because it has lots of good hints and tips of what we'll be expecting when we see your final reports. So we're going to leave you to read this through thoroughly in your own time, but a few things that we would like to highlight. Firstly is plotting. So you can have a look here at some of our expectations when you're plotting. You know, we want nice big plots so you can see all the data clearly. We have examples of bad plots and good plots. So you can see that our good plot here has axes labels with units, it has a figure caption, and the data is nicely spread out, and we have a box on. So if you're using MATLAB to generate your plots, just simply type box on into the command window. Tables, you want to make sure, particularly to be careful of any significant figures. We have examples here of good and bad tables. You can see here a good table is going to have grid lines. It's going to have headings with units up the top, and again, taking care of your significant figures. We're going to be asking you to do a number of schematics throughout this report. So when you're doing your schematics, we want you doing them by hand, on the computer, not by hand, and making sure you've got nice, clear labels for all the different parts of the experiment. So I will point out in your communication guide, there are some good examples of the FM1 experiment. Don't just copy and paste this, but you can use it as a nice guide to make sure you're getting all the components of the wind tunnel. This also shows us how we want to lay out any equations. Again, we have bad and good examples. If you look closely at the good examples, we have text before and after our equations. All of our variables are defined. And once we've defined our variable once, we don't need to keep redefining it over and over again. Assume that the reader has read it. We have equation numbers next to each of the equations. And we don't just list things. Again, you can have a look at these bad examples to see what we don't want. Lastly, we want you to be referencing while you're doing this. So we have some examples of in-text citations and a reference page entry. We recommend using the format used by the Journal of Fluid Mechanics, and that's what these examples are here. If you want further examples of how to cite in this style, you can look at this Cornell Help for Engineering Communication by Tracy Nathans-Kelly. Using this link at the bottom of your guide, that'll give you more citation examples. Okay, so we're going to start looking at your lab report now. So you should have each found online a copy of the lab report guidelines for our drag reduction by wake interference. So as Jay mentioned before, we're going to be stepping you through each of these different sections and telling you the expectations for each part of the lab report. So the first section you can see here is the summary. So the summary is actually going to be the thing that you write last. So you're going to do this once you've completed your whole report, then come back and write the summary. So the summary should be no more than 1 page, and it's going to encapsulate the whole report as it says here. So things that you want to include in your summary. So you want to have what you did in the lab, so what were the aims of the lab? As the lab name suggests, we wanted to decrease the drag force on our square cylinder. You want to include what equipment was used in the lab. So our beautiful blue wind tunnel, used pressure transducer, scanny valve, etc. you want to make sure you include the Reynolds number of the experiment. So this is going to be based on the height of the cylinder. We have given you already the equation for the velocity in the lab handout. We'll talk about this a bit later on as well. But you do want to mention in your summary that even though we're operating at a high Reynolds number, we don't have a turbulent flow, and we'll address this later. You want to talk about your data that you got compared to any previous experiments. So one of the plots that you did in your lab handout compared your data to that of Purdy, Sheridan, and Williamson in 1999. So make a comment whether this agrees or not. Going to talk a little bit about potential versus real flow, and we'll go into this in more detail later on. Talk about the different modes of wake interference. So we introduced this in the lecture and in the lab. So if you recall, these are cavity mode and wake impingement mode, and you want to talk about their effect on drag. And then lastly, include any practical recommendations. So what you've learned in this lab, how can this be applied in real life? So examples could be cyclists drafting behind each other, birds flying in V formations, things like that. So you want to make sure you're summarizing all the results that you found in this lab. For example, what optimum P over H did you find for the system? And as I said, you want to be concise and very precise with your summary. Try not to let it go longer than a page.
Okay, so after you're done with the summary section, you're going to want to do your experimental method section. And so in this section, we're going to talk about essentially how you measured your data and how you essentially calculated everything that goes in your lab report. So let's start off with how you actually measured your data. So we used the BBWT, the big beautiful wind tunnel, or maybe blue beautiful wind tunnel, possibly big blue wind tunnel, I'm not sure. It's one of those three though. So you're gonna want in your lab reports a schematic of this, and so you're gonna want to create this digitally, and it's gonna have to include certain things. So let's talk about what needs to be included. So let's go through the different components of the BBWT. Okay, so what we start off with is an inlet. This is obviously the inlet is where the wind comes in. So from the inlet, we have a honeycomb section. Now this honeycomb section exists to essentially decrease the turbulence, straighten out the flow, if you will. And so this actually does a fantastic job of doing this. It actually decreases the turbulence to less than 0.2%. So the turbulence intensity is less than 0.2%. So we have our inlet, we have our honeycomb. And so, like I said, it's less than 0.2% turbulence intensity after this. And here the flow constricts to accelerate into the test section. So we have a constriction right here into our test section. So we'll talk more in detail what's going on in the test section, but if you remember from the lab, we have our cylinder, we have a pedostatic tube, and we have a rack and pinion system that we put a plate on. Okay, so after the test section, we have our fan, and this is what's doing the sucking of the wind right here. So this actually drives the flow. And then after that, we have our acoustic diffuser, the fan here, and then acoustic diffuser at the end. If you remember from our FM1 lab video, this is where we had our lovely assistant James go in and kind of yell, and the sound diffuse. So works very well. In this section, like Sarah said earlier, the communication guide is very helpful because there's a schematic of the wind tunnel in that, which has all of these components and then some. And you're going to want to include a schematic with labels of this. Okay, so now we're going to go into more detail about the test section. And you're also going to need this schematic in your lab report as well. So we have our test section here. Okay, so we have our pedostatic tube. So if you remember, this measures the velocity by measuring PT minus PS. They're the dynamic pressure. We also have the cylinder here, their square cylinder. On our square cylinder, we have holes tapped on both the front face and the back face. And these holes all each have Tygon tubing along with the pedostatic tube that go to our Scani valve. And all our Scani valve does is just sample different Tygon tubing locations. So went from 1 to 20 and just sampled different locations. And whichever location was sampling, that was sent to our pressure transducer. Which measured our pressure and volts, and then from the pressure transducer, that was sent to software, which we controlled through LabVIEW, which recorded all of our data into an Excel sheet. So LabVIEW and Excel. Also in our test section, we had a rack and pinion system. And we use that system to move around our plates, which we used to study the wake interference. So that's the test section. You're going to need something like this, obviously neater than what I've drawn, but at least as detailed compared to what I've drawn. So some sort of schematic with labels for the test section as well. All right.
Okay, so the last part of your experimental methods is looking at the formulas and measurements that you make for a typical C p-value, and from this, how you get to CD. So to do this, you're going to need your lab handout, and we're going to be looking at the page of the pedostatic tube. So as Jay mentioned before, your pedostatic tube, the hole at the front of it is going to measure the total pressure, because this is a stagnation point. And the holes at the side of your pedostatic tube measure the static pressure. From Bernoulli's equation, we know that PT minus PS is going to be equal to half rho u squared, which is the dynamic pressure.
So ultimately in this lab, what we care about is the drag, but obviously we're not measuring the drag, we're measuring the pressures and then getting the drag from the pressures. So in your lab report, you're going to have to talk about how you get to drag from the pressures. So to begin with that, you're going to talk about pressure coefficient, because what we measure is the pressure at that location, the static pressure, and the total pressure. So to calculate pressure coefficient, we know that pressure is always measured relative to something. So in this case, it's measured relative to the static pressure. So measuring the pressure at that pressure tap location, and we're subtracting away the static pressure, and that's normalized by the dynamic pressure, which we know from Bernoulli's that's also just equal to PT minus PS. And so we measure this from our pedostatic tube. And then these are just sampled from our Scani valve. And so we can see that the pressure coefficient is just a ratio of two voltages. So just this voltage divided by this voltage, essentially. And so from this, we can calculate the pressure coefficient at each location. However, what we want is the total drag coefficient. And so we know that the drag coefficient is just the pressure coefficient integrated. And so we integrate from the bottom of the square cylinder to the top of the square cylinder for the front side, and we subtract away the pressure coefficient on the back side. But obviously, because we don't have continuous data, where pressure tap locations aren't just, we don't have infinite number of points, we have a finite number of points. We have discrete data, we can't just integrate, so we have to use discrete integration. And to do so, we are essentially just going to sum up our pressure coefficients multiplied by essentially this weighting function. And this is all in your lab manual. So to go from pressure to our final drag coefficient, we're going to use this formula right here. So in your lab report, you're going to derive this formula, and then you're also going to include a schematic of your pressure tap locations. So this is in your lab manual on this page right here. So you're going to, or actually, this is a better reference, this page right here. And so you're going to include something similar to this, a schematic of essentially your pressure tap locations that also shows what the weighting functions are, essentially, what you use to discretely integrate your data to get your final drag coefficient. Okay, so now that we're done with the experimental method section, we're going to move to section 3, which is the main body of your lab report, which discusses most of our results, the wake interference and drag reduction section. Specifically, we're going to start with 3.1, which is talking about the drag coefficient and pressure distribution for a bare cylinder. So if you look at your sheet, the first bullet point says, what is your Reynolds number? And so, as that suggests, you're going to have to calculate your Reynolds number for this. So the equation for Reynolds number is just written right here. So it's equal to rho u h over mu, with rho being density, u being the velocity of the free stream, h being the height of the cylinder, and mu being the viscosity. And what you're going to end up finding is that the Reynolds number is going to be somewhere in the range of 35,000 to 45,000, which is a very high Reynolds number. But just because it's high doesn't mean it's turbulent. If you remember from our experimental method section, we have the honeycomb there, which lowers the turbulence intensity to less than 0.2%. So really the turbulent intensity is really only going to be about 0.1, 0.2%. And so why is that? Why do we have a high Reynolds number, yet we don't have turbulence? So what you have to remember is that turbulence develops from the boundary layer. So if we look at our test section, and we look at where our test cylinder is, it's in the middle of our test section. But again, the turbulence develops from the boundary layer. So if we look at the boundary layers, if you look at how the boundary layers develop, you'll see that the boundary layers never actually reach the square cylinder. So even though there is turbulence in the test section, that turbulence never actually reaches the square cylinder. So the flow that actually the square cylinder sees is actually a fairly laminar flow.
So after you've calculated your Reynolds number, your handout then asks you to discuss real pressure distribution versus potential flow. So in this section, we recommend using diagrams to show the difference between potential and real flow. So if we first look at the potential flow over a square cylinder, if you recall, the assumptions of potential flow is that the flow is incompressible, irrotational, and inviscid. So when you draw your streamlines around the flow, they're going to be symmetric around the front and the rear of the cylinder. Because the pressure distribution is then going to be the same over the front and the rear, the drag force over a bluff body in potential flow is going to be equal to 0, and this is known as D'Alembert's paradox. In our bluff body flow, we have flow separation. So again, you're going to include a diagram. So you're going to have your square cylinder. We still have a stagnation point at the front of the cylinder. Then we have free shear layers, and we have the flow separating and forming vortices behind the cylinder. So we know that these vortices have a low pressure core, and we call this base suction. So this is going to be pulling the cylinder back and creating drag over the cylinder. Because we have these vortices shedding off the rear of the cylinder, we have fluctuations of the pressure at the back, and as you saw in the lab, the pressure over this rear face is going to be approximately constant. So when you talk about potential versus bluff body flow in your report, you want to make sure that you include your CP Baer plot, where you compared the potential flow to bluff body flow. And when you do this, make sure you reference where you got that potential flow data. So when you compare your CP Baer data to potential flow, make sure you reference where you got this data. So this is from Coy, and this is in your lab handout. Only on that page.
Okay. So in addition to what Sarah was talking about, describing what the flows look like for both the potential flow and the actual real flow, you're going to want to talk about similarities and differences between the two as well. So if we look at the pressure coefficients for the two cases, here red being the potential and green being the real, we can see that in some areas they are very similar, in some areas they're different. So this right here is the front face for the real cylinder case, and the rear face. And then obviously for potential flow, it's symmetric on both sides, so this represents both the front face and the back face. And so we can see that the front faces are actually pretty similar until we get towards the edges of the square cylinder. And the reason for that is if we look at our streamlines, we can see that they are similar. But remember, for the potential flow case, the streamlines stay attached to the airfoil the entire time, whereas we get flow separation for our real case. And so to stay attached, the streamlines would actually have to accelerate to velocities of infinity at the corners of the square cylinder for our potential case, whereas that doesn't happen in real life. And so that explains the divergence as you get further away from the center point. Obviously the rear faces are very different, so with potential flow the rear face is exactly symmetric to the front face, and so we can see that there's only one line there, whereas as Sarah said, the rear face for the real cylinder, you get a very constant low pressure across the back face, which creates this suction. In contrast, for the front face, you get a high positive pressure. And so drag is actually the difference between drag is actually the area between this front face and back face, essentially. And so you can see that because we have positive pressure on the front face essentially pushing our cylinder, and then a negative pressure on the back face sucking our cylinder, we have a lot of drag. Whereas in our potential case, as Sarah mentioned, we have zero drag because it's exactly identical between front face and back face. Okay, so in this section we're going to talk about blockage, and so blockage will affect the drag values that you're calculating. So as it says here, the flow is affected by the walls. So essentially blockage wouldn't be a problem if we had an infinitely large test section, but obviously that's not the case. So what ends up happening is basically to satisfy continuity and maintain conservation of mass, the flow has to actually accelerate around the airfoil. And so this creates a couple effects. So number one, our pedostatic tube is pretty far upstream compared to where the square cylinder is. So the velocity measured by the pedostatic tube is actually lower than the velocity that the square cylinder experiences. And so because the flow going around the square cylinder is actually faster than what we measure, that actually increases the drag that way. On top of that, we're artificially measuring higher drag because the velocity that we're actually measuring is lower than the velocity seen by the airfoil. And because of that, because of how we normalize things by 1/2 rho u squared, we're using a lower velocity than what is actually hitting the airfoil, and that also increases drag. In essence, the drag that we measure is artificially higher because we normalize by a lower velocity than what the cylinder experiences.
So the next part of blockage in your lab report handout now is computing a corrected CP value in a table. So the way that we correct for our blockage is by using two different methods. The first method being an equation by Mascal, and later on we'll look at a method that you will derive yourself. So in Mascal's method, the equation for the corrected coefficient of pressure, so CP corrected, is equal to the measured CP value times by 1 minus 1.5b plus 1.5b. So in this equation, b here is equal to little h over big H. So this is the ratio of the height of your cylinder to the width of the test section. And for our experimental setup, this is equal to 0.11. So the way that you're going to include these coefficient of pressure corrections, as I said before, is in a table. So using your data sheet that you had for your bare cylinder, you're going to add a new column next to CP called CP corrected. And you'll also have a column of CP corrected times the weighting function. And when you sum up CP corrected times the weighting function, you can find CD corrected.
All right. So for method 2, we're going to call this the you do you method. So ultimately what we want to calculate is a function for CD corrected, which will be a function of the CD measured, and B, which is your blockage value. And so to get there, we're going to give you some hints. You're going to use continuity, so using conservation of mass. You're going to assume that the velocity profile is uniform, so it'll go from this U, which is uniform, to this U effective, which is what the square cylinder sees, which is also uniform. And then knowing that the drag equation, or drag coefficient equation, is drag divided by 1/2 rho u squared h, and knowing that the blockage factor is little h over big H, with little h being the height of the cylinder and big H being the height of the test section, you should be able to derive an equation for CD corrected, which is just a function of the CD measured and our blockage factor. Okay. And just the further hints, with your drag coefficient, we know that drag will be the same for both the measured drag will be the same for both CD measured and CD corrected. Really, all these terms will be the same. What's changing is your velocity term right here, which you can calculate from continuity.
Okay, so we now have two different ways of correcting for blockage. We have your method and Mascal's method. So as you saw before, you're going to find an expression for CD corrected divided by CD measured. There's a function of B. This should also give you a hint as to what your equation's going to end up looking like. Using Mascal's equation that we saw previously, we can also find CD corrected divided by CD measured as a function of B. I just want to point out here that you can't just change all the CP's in Mascal's equation to be CD's. Make sure you actually use the definition of CD to come up with this expression for CD corrected over CD measured as a function of B for Mascal. Once you have both your and Mascal's expressions, we're going to get you to plot both of these on the same plot. So we're going to plot CD corrected over CD measured against B for both you and Mascal. And you're going to have just a quick discussion included in your report here of which method you think is better. So a hint that we will give you here is have a look at what these plots look like at B is equal to 0 and B is equal to 1, and use these points as a jumping point for your discussion.
Okay, so that was section 3.1. Now we're going to move on to section 3.2, where we talk about mechanisms for drag reduction by wake interference. And you'll see 4 bullet points here. We're actually going to discuss things a little bit out of order. As first, we're going to talk about physically what's happening in the wake impingement mode and the cavity mode. Talk about how that reduces drag. So we're going to do the third and fourth bullet points first, and then we're going to go back and do the first 2. First we're going to start with the third bullet point, basically talking about what the wake impingement and cavity mode are, before we kind of discuss what it does to the drag. So to begin, we're going to actually kind of review what's going on in the bare case cylinder. So with the bare case cylinder, or bare cylinder case, sorry. Remember, we have essentially our flow coming in, hitting the front face of the cylinder. It's creating a stagnation point in the middle. At the 2 corners, the flow separates, creating these free shear layers that roll up into low pressure vortices. So this creates low pressure on the back face and high pressure on the front face. And so the combination of low pressure on the back face and high pressure on the front face both contribute to drag. So that's why we see a lot of drag in the bare cylinder case. So now we'll talk about the cavity mode. So the cavity mode occurs once we introduce a plate and the plate is not too far away from our square cylinder. So essentially what happens here is now the plate, the flow is separated from the plate, but actually the streamlines from the plate will reattach to the corners of our square cylinder, and they'll stay attached. And that creates a very low pressure cavity here, right here, where we actually have 2 low pressure recirculation vortices. And these vortices are stable because they constantly have energy fed in via the shear layers coming off of the plate. And so these low pressure vortices are very stable, and they actually decrease the pressure on the front face because they're low pressure vortices. These streamlines attach to the corners of the square cylinder and stay attached. And because they stay attached, our wake here is thinner compared to our wake for our bare cylinder case. And because it's a thinner wake, we create weaker low pressure vortices on the back face, which actually increases our pressure on the back face relative to our bare cylinder case. And so the combination of lowering the pressure on the front face and increasing the pressure on the back face causes a significant drag reduction for the cavity mode. Going to the wake impingement mode, we've now increased the distance between our plates and our cylinder. And so now we're still getting shedding off of our cylinder, off of our plate, but our plate is now far enough away from our cylinder that these streamlines can't attach to the corner or reattach to the corner, creating that very stable low pressure cavity that we saw in the cavity mode. Instead, we're going to get this. We're going to get a wake from the plate of low pressure vortices, and these low pressure vortices go downstream and impinge onto the face of our square cylinder, which is hence the name wake impingement mode. Now, because these low pressure vortices are lower pressure than the flow that we saw in our bare cylinder, this actually decreases the pressure on the front face as well. And so these low pressure vortices will continue to flow downstream and actually disrupt the wake formation of the cylinder. And so because it's disrupting the wake formation of the cylinder, we actually create a weaker vortices in the wake of the cylinder. And so that actually works to increase the pressure on the back face of our cylinder. And so again, with the combination of decreasing the pressure on the front face and increasing the pressure on the back face compared to the bare cylinder case, we actually decrease the drag in our wake impingement mode. Now, a comparison between the cavity mode and the wake impingement mode is that these low pressure recirculation vortices are very low pressure compared to these the wake from the plate impinging on the front face of the cylinder. So you actually get a significantly more pressure decrease from this low pressure recirculation mode than you do from the wake impingement mode. So you actually get more drag reduction on the front face, and then the two rear faces have about the same pressure, even though they have different methods of getting there. And you'll see that when you plot the pressures of the cavity mode and the wake impingement mode.
So in your section 3.2, you also have to compare your data of the bare cylinder versus your plots with your 37% plate at plate distances of 1.5 and 4.0 in front of the cylinder. So we want to talk about which of the two modes results in better drag reduction, cavity mode or wake impingement mode as well. So when you're looking at your 37% plate at a G/H of 1.5, we know that we are in cavity mode. So when you plot this, there's a few things that you want to take note of. Firstly, when we compare our plate, our data with the plate in front of it to the bare cylinder, we notice a big decrease in drag as we expect. So the front face, as you saw from Jay, is going to decrease dramatically because of those recirculation vortices in front of the cylinder. And then the rear face is also going to increase relative to the bare cylinder due to that weaker vortex wake. And you can see here, this area in between the front and rear faces is going to be our CD, because we know that our CD is the area between our CP front and CP rear. If we look at our CP plot for now our G/H of 4.0 for the 37% plate, we are now in wake impingement mode. So again, you're going to be looking at your data with the plate compared to the bare cylinder. So if you look here, our rear pressure data is going to increase relative to our bare cylinder. Once again, we have a weaker vortex wake than the case of the bare cylinder. And you'll notice that this increase is pretty much the same both in cavity mode and wake impingement mode. In our wake impingement mode, once again, we have a decrease in the pressure of the front face of the cylinder. But we notice that it doesn't decrease as much as it does in the cavity mode. But we still get this decrease because of those wake vortices formed behind the plate, so that von Karman vortex streak impinging on the front face of the cylinder. And again, our coefficient of drag is going to be the area between the front and the rear. So if we're having a look at our cavity mode and wake impingement mode, we can see that cavity mode is going to result in better drag reduction. Okay, so the last point of 3.2 that you're going to be doing is discussing CD over CD bare versus G/H for your two plates, 13% and 37%. So this is the plot that looks like this. So a few things that you want to take note of when you do this plot. Firstly, we're going to be labeling our different modes. So cavity mode is going to lead to this big drag reduction. And then wake impingement mode is at the higher G/H's. And you notice in the middle, I've labeled this section IS. So this is our intermittent switching. And online, you should have a page to download that looks like this. So this is our intermittent switching. So when you're putting intermittent switching on your plots, couple of things you want to be careful of. You want to make sure that these lines don't extend past the intermittent switching, so make sure you've got defined corners. And make sure none of your data points are included in that intermittent switching region. So going back to this plot that you have online, as I said, this is evidence of our intermittent switching. So we touched on this briefly in the lab, but what intermittent switching means is that in this middle region here of G/H, our flow is just swapping back and forth between cavity mode and wake impingement mode. So it's going in between forming these recirculation vortices and then having those wake vortices impinging on the front face of the cylinder. So it's important to note, and we've got it written on the sheet for you, that this is intermittent switching and not hysteresis. So as you're finishing section 3.2, we just want to reiterate that it's important when you are talking about your cavity mode versus wake impingement mode, make sure you talk about the effect on both the front face and the rear face of the cylinder. So it's the decrease of pressure on the front face relative to the bear and the increase in pressure on the rear face relative to the bear that combined lead to that drag reduction.
Okay, so that was section 3.2. Now we're going to move on to section 3.3, where we're going to talk about the optimum drag reduction. So to get to that point, if you remember from the lab, we increased plate size to 50%, and we saw that at 50% we are actually generating thrust. So it's interesting that as we increase plate size, we get more and more thrust, or less and less drag, until the point we actually get thrust. And so you're going to include a plot of CD over CD var versus P over H to see how increasing P over H affects CD over CD var. And on that plot, you want to label the point at which you go from drag to thrust, because that is a very interesting point. At that point, you can actually generate thrust by basically decreasing the pressure with the cavity mode. But obviously, even though we're generating thrust on our cylinder, for our entire system, we're not generating thrust. Otherwise, we'd all be very rich right now. Instead, what we want to calculate is the drag of the system, so CD system. So you want to derive the equations for CD system. That's in your lab handout, actually on this page. So you're going to use this page for reference to derive the equation for CD system. And basically what we want to see is a plot of CD system over CD var versus P over H. And you're going to find what the optimum location of your optimum plate size is for drag reduction. And so we can see that here presented are two options for the shape of the plot, essentially. So this is a very narrow region with the x-axis being P over H and the y-axis being CD system over CD var. And so here we're presented with two options, one with a very narrow region of which P over H's lead to significant drag reduction, and the other one being a very wide region. And so bring up the question, which shape is better from a design perspective? Obviously, when you have a wide design range, that's always better. So when you actually plot it out, you'll see that it is a fairly wide region. So we want you to basically pick the optimal drag reduction. So basically pick which location it is from this wide region. So you're going to have to kind of talk about your thinking here in terms of why you picked a certain location. Maybe you pick the absolute minimum in terms of drag, or maybe you pick something that's closer to the left side because that's a smaller plate and you can save material when designing something with the smaller plate. Anyways, we'd like to see your reasoning behind what you pick as an optimum drag plate size.
Okay, so for the second last part of your report here, you're going to have your conclusion or concluding remarks. So here you want to include a summary of drag reduction by wake interference. So include your two modes, wake impingement mode and cavity mode, and a discussion on how both of these lead to drag reduction. You want to include whether we succeeded in meeting our aims of the experiment. So did we manage to decrease drag by wake interference? Also include what your optimal conditions were to decrease drag, so your main results that you found. At the end of the conclusion, we also want you to include 1 to 2 paragraphs of practical applications. So be creative here, use Google, come up with as many ideas as you can where you think this concept could be used in a practical application.
Okay, for the last part of your report, you're going to include this postscript. So you can think of this as like an exercise to do to just see how well this works in practice. So with the postscript, essentially what we have is a truck is following behind a car that's 37% the height of the truck, which is convenient because you have data with a plate that's 37% that of a square cylinder. So you can approximate this as a square cylinder behind a plate. If the truck were alone, it would be traveling at 65 miles per hour. But now that it's in this convoy, we want you to calculate what the new velocity would be, assuming that it's outputting the same amount of power. Now, power is just the force times the velocity. So essentially, this will be force times the velocity of the truck alone is equal to the force times the velocity of the truck in the convoy. And we know that the forces from this will be the drag. So the force in this case is going to be drag. So use this to calculate what the new velocity would be, assuming that you're in the convoy outputting the same amount of power. So the assumptions are that this car in front is conveniently 37% the height of the truck, which we have data for, and then also the distance between the car and the truck is always spaced such that the drag is minimized on the truck.